So we're going to kind of continue with chapter 38, where in 38 we talked about how light can behave both like a wave and like a particle. And now we're going to talk about how particles definitely have particulate nature, but they also have wave nature as well. So I'm actually going to start off by talking about how our model for the hydrogen atom has evolved, and that's going to be really important when we realize that it has some shortfalls, and it turns out that we need to actually treat electrons like waves in order to fully understand what's going on. So I'll talk about just all the various models of the atom, including probably the most common one, the Bohr model of the hydrogen atom. And I'll mention very briefly about how lasers work and how we can actually get black body spectra. And I'll finish off by talking about how Heisenberg's uncertainty principle is going to apply to particles as well as photons. So I mentioned this last time, in the late 19th century we had Maxwell's equations, and light was definitely a wave and matter was definitely particles. However, we soon found out in the early 1900s that light could have particle characteristics, so photons from the last chapter. It turns out that matter can have wave characteristics as well, and kind of the most common example of that is we know we can't see things that are really small, such as this little chunk of DNA. Note the scale down there, that's 100 nanometers. In order for us to be able to visualize this, we actually can use something like an electron microscope, which makes use of the fact that electrons have wave nature as well as particulate nature. So before I go on, I want to talk very briefly about this little Phet simulation, which is really cool. Here we have a box of hydrogen, and we have a light that I can kind of turn on and off, and I'm just going to leave it as white light. And what happens if we shine some white light, or all frequencies of light, onto a box of hydrogen? You can kind of see that some of the light's passing right through the box, some of it might be absorbed, and you can see occasionally, there was one right down here, where we had some light kind of come shooting off of this box of hydrogen. And if I kind of speed this up a little bit, you can see that most of the time we have one of those violet looking chunks of light come off, but occasionally we can get maybe some blue light or some red light spitting out of this box. And I've had this running for a while, and you can see most of the light coming off of it is in the ultraviolet. This is in nanometers down here, and this is a spectrometer, so it shows the spectrum of light that's coming out of this box of hydrogen. And we can have some purple, some blue, some cyan, and some red, as well as some IR. And the question is how come it seems like only these colors are coming out of this box of hydrogen? And that's going to lead us into talking about some various models of the atom. So let's talk a little bit about atomic models. And this little picture right over here probably looks kind of familiar. This is the Bohr model of the atom, and essentially we have this positively charged nucleus where we're going to have protons and neutrons making up the nucleus, and then we're going to have electrons that exist around this guy, and they kind of exist in these discrete shells, these discrete energy levels. And there's only a certain number of electrons, those are these blue guys, that can kind of live inside of these shells, and the first one is always going to be 2. So we've got these guys orbiting it just like planets going around the sun. Now, one thing about these models is when we come up with a new model to explain things, it needs to explain past things as well as kind of add things to previous models. So as we come up with models for the atom, it has to be able to explain kind of new things that we can observe. So here's a very brief little timeline of atomic theory, and not all the important players are in here, of course, but it kind of serves the purpose for the road map I want to take you on. And we've always been interested in what matter is made out of, and the Greeks had 2 theories. They had the theory that we could split a stone, split it again, grind it into sand, split it again, and that we would eventually come up with something that couldn't be split anymore. And this fellow right over here, he said that that was an atmos, which sounds a lot like an atom. However, Aristotle's theory that there were 4 elements kind of won for about 2,000 years, where we had land, air, fire, and water. And in the 1800s, a fellow by the name of Dalton kind of came back to the theory that we had atoms, something that could not be split into any smaller particles. However, this fellow right over here, J.J. Thomson, he kind of realized that atoms were made up of other things, and Rutherford discovered some of those things. Thomson discovered some of the other ones, and this led us to kind of the theory of the atom that I showed you on the previous page, designed by Niels Bohr. And then we kind of improved upon that by the work of a fellow by the name of Schrödinger, who came up with a wave model. So what I'm going to talk about for the next several slides is kind of who are these men, and how did they lead us on our map to discover what all of matter is made up of. As I said, I'm not going to try to butcher this fellow's name, but was about 2,400 years ago. He said, could we keep on dividing matter into smaller pieces, or is there a limit to how many times we could divide it? And he said, yes, there is a limit, and we're going to divide things and divide things and divide things, and finally we would get to this chunk that would be indivisible, and it would be the smallest piece of matter, and it would be the building block of all matter. And he said that the name means it could not be cut anymore. However, the philosophers Aristotle and Plato were more well respected and had this theory right over there, the four elements theory, that generally won for a very, very, very long time. Then this fellow by the name of John Dalton performed some experiments that eventually led to the acceptance that there were these things that were called atoms. And John Dalton's theory sounded a lot like the Greek philosophers. He said that we can have these atoms, and they're the smallest piece of matter, and we can't go ahead and split this guy up into two. And if we have atoms of the same element, then they're going to be exactly identical, and we can combine atoms to make different molecules, compounds, and stuff like that. And of course, different elements have different atoms, and to form these compounds and molecules, we have to do some chemical reactions. So it kind of made sense for everything that we knew at the time. However, in 1897, this fellow by the name of J.J. Thomson was performing some experiments that had nothing to do with atoms, but was kind of the first hint that the atom was made up of other particles. And what he was doing is he was studying some electrical current going through a gas with something like this, where we had an anode and a cathode and just a tube full of gas. And as current was kind of going through this gas, what he kind of found out is it was giving off these negatively charged particles. And he was kind of like, wait a minute, the atoms of this gas were uncharged, and so kind of what he said is Whiskey Tango Foxtrot, where the heck did these negative charges come from? So what Thomson kind of said is these charges had to come from within the atom, and so what that means is something smaller than the atom had to exist, and so the atom is divisible. And that's really, really, really a big breakthrough. And so what he did is he actually called these guys corpuscles, although today we actually call these negatively charged things electrons. And one thing that we knew is the gas was neutral, and so if these negatively charged particles are coming off of it, then there has to be something positively charged in the atom as well. But J.J. Thomson could never find them. So Thomson proposed a new model for the atom, and it's usually called the plum pudding model. You could think of it more like raisin bread. Plum pudding is an English thing. And what he did is he said, okay, we're going to have this blob. This blob is called the atom, and inside of this blob is going to live some electrons as well. There's got to be something positively charged in there as well. And these electrons are kind of scattered throughout it, kind of like raisins inside of some plum pudding. So let's very quickly pop back to my little Phet simulation here and talk about these first two theories if we were to look at light shining into a box of hydrogen. And if we had the standard billiard ball model, which is going to be the Dalton model, the light that is hitting the atom is bouncing off of it because atoms are hard and indestructible. You can kind of see all the light flying off of it, and the light that hits it is going to be coming off of it with the same frequency or the same color that was instant upon this ball, and that's not the case. We saw what really happens is we tend to see a lot more of those purple lights coming off it than some of the higher frequencies. If we were to take a look at Thomson's model, well, it's a little bit better. If we were to shine some light onto this model, we can excite this electron, but still it can only spit off the same frequency as that was incident upon it. So that's not going to work as well. So we're going to need to find a better model. Now, before we get to those other models, first want to kind of take you into how we discovered the fact that an atom must have a nucleus. And it was this fellow by the name of Ernest Rutherford, and he was actually doing something that had very little to do with figuring out what matter is made out of. What he was kind of doing is he was shining some positively charged alpha particles, which is essentially a helium nucleus, into some very thin gold foil. And what he found out was most of the particles passed through with little or no deflection. However, some of them were deflected, and very, very, very few were widely deflected, and some of them were actually directed nearly directly backwards. So he had some radioactive substance right over there, kind of spitting some alpha particles, and here's the gold foil right over there. And as I said, most of them passed right through it, but some of them were bent off at some weird angles, and very, very, very few were scattered directly backwards. So what that kind of meant is, or what that kind of meant is that Thomson's model was wrong. Thomson's model only allows an alpha particle to be scattered through a teeny tiny angle. Kind of remember this guy is positively charged, and here we have the positively charged plum pudding with some negatively charged electrons through there. There is no way for this positively charged alpha particle to be reflected backwards. It's only going to be deviated by a small angle because like charges are going to attract, and there's some negative charges in there, and so everything's going to kind of balance out. So what Rutherford kind of realized is that there has to be all the positively charged particles concentrated in this teeny tiny thing that he called the nucleus, and the electrons have to kind of be on the outside, and the alpha particles that were directed backwards hit the nucleus and kind of bounced back like that. Most of them, maybe they passed right here and they were attracted, and so they went like this. And since an atom is mostly empty space, then most of them just pass right on through. So this slide pretty much says everything I said in the last slide, but Rutherford essentially discovered that atoms have to have a nucleus, and all the positive charges have to be concentrated in this little teeny tiny area, and the electrons are going to kind of be around it, balancing out the charge. And so he said, okay, most of an atom is made up of empty space, and that is true. We know that this is about 10 to the minus 15th meters, and this right over here is 10 to the minus 10th meters. So it's kind of like our solar system. There's a sun, and then there's a lot of empty space, and then we have the various planets. When they hit the positively charged core, then we had the backscattered alpha particles, and so he said this must be really tiny, it must be positive, and the electrons have to live outside of it. Now, Rutherford's model was missing one important thing, and what that thing was is, how are these how do the electrons live inside of these orbits? And the key to that is to take a look at atomic spectra, which is essentially shining some light onto some hydrogen and seeing what color light comes flying out of that box. And something that people observed is that if we were to look at the colors that came off of hydrogen, or the hydrogen spectrum, that we were going to see, well, some light in the UV, just like we observed, and then we're going to see several distinct lines where we're going to have some red lines, we're going to have some blue lines, we're going to have some violet lines, all the way up into, ultraviolet. And something that we kind of noticed is that the spacing between the successive lines got smaller and smaller and smaller and smaller until they kind of merged. So that's kind of this picture that we're looking at right down here. Now, it turns out that mathematicians were able to figure out some mathematical formulas that could figure out the wavelength of some or some of these lines. But the problem is we have these formulas, we know that they work, they can predict the colors that we're going to see coming off of some hydrogen, but we have no idea why. Something that a fellow by the name of Rydberg noticed is that you can essentially add the frequencies of two lines that are in series, and that very often equals the frequency of the third line, and that's actually going to be a conservation of energy thing. This is actually known as the Ritz combination principle. It took a fellow by the name of Niels Bohr to kind of come along and explain this, and what Niels Bohr said is these energy levels inside of a hydrogen atom are going to be quantized, and what that means is that these electrons are going to live inside of very discrete orbits called shells. So this finally leads us to Niels Bohr's theory of the atom, which builds upon Rutherford's, that we're going to have a positively charged nucleus, and we're going to have electrons that kind of orbit around this guy right over there. And what Niels Bohr said is these electrons have to orbit in very discrete shells, and he said that this is going to be the ground state, n is equal to 1, and then this one over here is going to be n equal to 2, and then kind of so on and so forth, n is equal to 3. And so these electrons occupy these stationary states that are of fixed energy, not fixed position, away from the nucleus. And electrons can make jumps between one energy state and another, and when they do, they're going to emit this thing called a photon, or light. And how much energy they jump is going to be related to the frequency. So if we were to pop that guy away for a second, look at these states, n is equal to 1, n equal to 2, n equal to 3. If we had an electron way up here in the n equal to 3 state, then it can do two things. It can drop down here to the n equal to 2 orbit, or it could drop down to the n equal 1 orbit. And kind of the energy difference between these two states is going to be related to the frequency of the light using Planck's constant. And this looks a lot like something we saw in chapter 38. And what he kind of did is he realized that the ground state is going to have some negative amount of energy right over there, and then these are going to have less and less and less negative. You kind of think of these electrons as wanting to fall down into a well, just like objects tend to fall down into Earth. So if at all possible, electrons want to live in the n is equal to 1 state. If we had an electron that was hanging out right over here and it dropped down into the n equal 1 state, then it's going to emit a photon. And you can kind of see here we have the red, the green, and the blue. You can convince yourself that those colors actually represent the energy difference between these various states. Of course, the closer we get to blue, the more energy we're going to have. And this would give us essentially a red line, a green line, and a blue line, but still the very distinct spectra that we would expect to see. So you can convince yourself that the ground state and then the first two excited states will have these energies using the expression on the previous page. I will also mention that you will see this in electron volts as well. So what would we expect the wavelength of a photon to exist if we had an electron that was sitting at the n equal 3 state and dropped down to the ground state, or the n equal to 1 state? So you could convince yourself that we're talking about a change in energy that's going to be equal to the final minus the initial, so negative 22 minus negative 3 times 10 to the negative 19th, and that's going to be equal to negative 19 times 10 to the negative 19th joules. And the energy that this electron loses is going to be gained by a photon, so the photon is going to be the same number, but that's going to be a positive. And so we're going to say that this delta E now for the photon is equal to h times f, Planck's constant, times the frequency, or hc over lambda. And so lambda is going to be equal to h times c divided by delta E. And so this is going to be 6.626 times 10 to the minus 34th multiplied by c, 3 times 10 to the 8th, and divided by that energy change, 19 times 10 to the negative 19th, and we're going to get 104.6 nanometers, which is in the blue, or UV, as we kind of expect it to be. Keep in mind you could do this for the n equals 3 to the n equal 2, or the n equal 2 to the n equal 1 state as well.